Am I audible? Please let me know if I'm audible or not. Am I audible? Okay, let's wait for a couple of minutes for more participants to join. After that, we'll start. Please let me know if you can see my slide or not. Let's wait for a couple of minutes. After that, I will start. Okay, so let's get started. So today is our 12th NPTEL live session, and today is our final session of Advanced Foundation Engineering course. Well, so till now we have conducted 11 problem solving sessions, live sessions. I hope you have all, yeah, I hope you have all understood the problems very. I hope you guys have understood the problems very well and how to solve the problems. And and I hope you have also gone through all the lectures. And if you have any problems, you can either mail me or you can post your doubts in the NPTEL forums also. And you can also personally mail me in my mail address. And exam is also around the corner, so I believe you can also go through the recorded sessions because all the sessions are available on YouTube and the link is given on the NPTEL website. You can also access the lectures from there. And if you have any doubts regarding anything, you can just visit them as you like, whenever you like. Mm, okay, so today I'm going to conduct another revision session. So in the last revision session, I solved some problem related to shallow foundations, and in today's revision session, I'm going to solve some problems related to pile foundations. Okay, so and please follow today's session very carefully because I'll be explaining the pile foundations once again from the beginning, and I hope this will help you for your upcoming exam. Okay, and also it will help you to build up your concepts. Okay, so please follow the lectures carefully. Okay, so let's get started. And before starting, let me introduce myself for one more time. My name is sinjandebnath. I am a PhD student in the Department of Civil Engineering at IIT Kharagpur, and I welcome you all to this session, to the final session. Okay, so let's get started. I hope you can all see my screen, my slide. Okay, so before starting pile foundations, I'm going to just brief about the pile foundation once. I'm just going to write down all the formulas that we will use for today's problems, and I'll also brief about the concepts one more time. Okay, so pile foundations. So pile foundations. So as we have discussed earlier, pile foundations, well, these are deep foundations where the depth of the foundation is much greater than that of its breadth, and it is embedded into the soil to a greater depth. And when it is used, suppose there is a weak layer, and over shallow foundation construction is not possible because there will be differential settlement, or uh, maybe it will maybe due to differential settlements and other general shear failure cases, and maybe shear failure cases, okay, bearing capacity failure, or maybe differential settlement, anything. Okay, so in that case, so what we need to do is that we need to construct this pile foundations in order to transfer the structural load into firm soil, okay, beneath the weak soil. Okay, generally we use pile foundations for that. Okay, in order to transfer the load from the superstructure to a firm strata. Okay. Okay. So pile foundations. Well, so the ultimate bearing capacity of pile foundations, QU. QU is the ultimate bearing capacity, the ultimate load carrying capacity of a pile foundation. Okay. It has two parts. Okay. It has two parts. One is tip resistance, and another one is frictional resistance. Okay. So QPU, it is the total tip resistance plus QF. Okay, so QP is the total tip resistance or end bearing resistance, and this one is the frictional resistance, total frictional resistance. Okay, so actually what happens is that generally pile the a pile foundation derives its capacity, its load carrying capacity from these two, from these two parts. Okay, so actually it is like this. Suppose this is your ground surface, okay, and you have constructed a pile foundation over here, and suppose you have a farm strata over here, okay, like this. Suppose this is your not so dense soil, suppose weak soil, okay, weak soil, and here it is farm soil. So in where, suppose you are applying, suppose here is the pile cap on the top of the pile, and you are applying load on top of the pile cap, okay, it is carrying superstructural load. Okay, so suppose this is the pile, okay, this is a pile cap, and the superstructural load is acting on top of the pile cap. Okay, so how it will distribute the load? So see, first of all, there will be skin friction along the length of the pile, okay, skin friction along the length of the pile, and also there will be end bearing resistance. Okay, so it is exactly I mentioned over here. See, the ultimate load carrying capacity of pile has two parts. One is total tip resistance, and another one is frictional resistance. Okay, so suppose you are applying load like this q, and it will be, and this load, suppose you are applying load like this, and load is carried into two parts. Okay, one is frictional resistance, QF, total QF. It will act, this frictional resistance acts along the length of the pile. And another one is end bearing resistance. Okay, this one is QPU. This one is end bearing resistance. Okay, and this will be provided by the farm soil. Okay, by the farm soil below the weak soil. Okay, it is like this. Now, now suppose Now, suppose this farm soil, this is a pile foundation. Okay, now suppose the farm soil is at a greater depth, and this load, suppose the superstructural load Q is only carried by the QF part, that is the frictional part. Okay, that means suppose where only this QF dominates. Okay, in that case, where only QF dominates, and because the farm strata is at a very lower depth, and to construct a very long pile is very uneconomical. In that case, if we construct a pile of substantial length, then it will provide enough screen friction to to carry out the total load, super total structural load. Okay, suppose QF. So in that case, when this QF is the dominant one, in that case, it is this type of pile is known as frictional pile, or floating pile. Okay, frictional pile or floating friction pile or floating pile. Okay, and when suppose this weak soil, so suppose there now another case, suppose there is a farm soil, and this pile is resting on top of the farm soil, and suppose this weak soil can't provide the skin friction. Okay, there are cases when the soil is very weak and the soil can't provide that skin friction. Okay, very loose soil, suppose very loose sand, in that case it will not provide, it will not provide great skin friction along the length of the pile. Okay, and in that case, this q will be only carried by the tip resistance, that is qpu. Okay, whenever this qpu is dominant, in that case the pile is known as end bearing pile. Okay, I have already explained these things in the previous lecture. You can visit the previous lectures in order to understand these concepts. I am just rebriefing it once again. You can also see the NPTEL video lectures of Professor KD, Professor Dev. Uh, you can also go through the concepts by visiting. You can also understand the concepts by go through the lectures once again. Okay, so this is the basic concept. Okay, now let me just write down the equations that we will use. So the ultimate load carrying capacity of a pile, it is defined, as I told earlier, it is defined by two parts. Okay, so load will be carried into by two parts. So one first part is what? QPU, that is the tip resistance, total tip resistance, and another one is the screen friction resistance, total screen friction resistance, that is QF. Okay, now these two can be written like this. Okay, QPU AB and FF into AS. And what is QPU and what is FS? So QPU is the unit tip resistance or unit end bearing resistance. Okay, unit tip or unit end bearing resistance. And this QPU is actually QPU. This capital QPU is equal to small QPU into AB. What is AB? AB is the cross sectional area of the pile. Okay, cross sectional area of the base of the pile or the cross sectional area of the pile. Cross sectional area of the base of the pile, particularly when the pile is tapered. Suppose the diameter of the pile, the tip of the tip diameter and the base diameter is different. Okay, in case of tapered piles, in those cases we will take the area of cross section of the base. Okay, in other cases, if the diameter is uniform throughout the length of the pile, in that case we can take the cross sectional area. Okay, just a cross sectional area at any depth. Okay, so it is like that. So now EFS, what is FS? FS is the unit screen friction resistance. And what is AS? AS is the surface area of the pile. Okay, surface area of the pile. Now, one thing I would like to mention. Now, one thing before going into the equations, one thing I'd like to mention. Uh, we know the ultimate bearing capacity for shallow foundation. Okay, the ultimate bearing capacity of shallow foundation, the Tarzaki's equation. So let me write it down once again. See, this one is tip resistance. Okay, you need see this portion. Look at this portion. Okay, it will provide the base of the pile. The tip of the pile is resting on top of the farm soil, and it is providing end bearing resistance. Okay, it is more or less similar to that of the shallow foundations. Okay, so what is the basic bearing capacity equation for shallow foundation? So QPU for shallow foundation, it is CNC plus sigma dash NQ plus 0.5 comma BN gamma, right? This is the equation, ultimate bearing capacity equation for shallow foundation, right? So these two parts are much greater than this part. Okay, so this part can be ignored. Okay, this part can be easily ignored. So QPU can be written like this. Okay, CNC plus sigma dash NQ. Okay, now see. Now, if the soil is cohesive soil, okay. Now, if the soil is cohesive soil, in that case, so if you remember the previous lectures, you will see in case of cohesive soil, this part becomes zero because NQ is zero. Only this part remains. Okay, so that means for cohesive soil, QPU is CNC. Okay, and in case of cohesionless soil, and in case of cohesionless soil, this C becomes zero. Okay, only this part remains only because C becomes zero. So in that case, for cohesionless soil, we can write like this. So QPU is equal to sigma dash NQ. What is sigma dash? This sigma dash is the effective overburden pressure. Okay, and what is C? C is the cohesion. NC and NQ are the bearing capacity factors. Okay, so these are the two equations. Okay, and also I'd like to mention one thing. These two are QP. Okay, and what about FS? Okay, so we have determined this QPU and QPU for cohesive soil and cohesionless soil. And one thing also like to mention that for cohesive soil, this C and C, this C is taken as 9. This NC is taken as 9, the bearing capacity factor. Okay, it is generally 9 CP. It is denoted, this C is denoted as CP. Okay, and the cohesion part, and NC is equal to 9. Okay, okay. So we have discussed about this QPU part. Okay, that is the unit tip resistance. So what about unit screen friction resistance? That is the FS part. That is this part. We have determined this part. Okay, but what about this part, this FS part? So FS. So for cohesive soil, So for cohesive soil, this Fs is equal to alpha into C dash. What is alpha? Alpha is the adhesion factor. And what is C dash? C dash is the cohesion along the length of the pile. Suppose like this. Suppose you have a pile like this, and this is your farm strata. Okay, farm strata. In that case, C dash is the cohesion of this soil layer. Okay, a cohesion is this C dash is the cohesion of this layer. Okay, and this Cp is the cohesion of this part of the farm strata. Okay, this Cp is the cohesion of the farm strata, and C dash is the cohesion of this along the length of the pile of okay, of this layer. Okay, so for cohesive soil, this Fs, that is the unit skin friction resistance, it is alpha into C dash, while alpha is the adhesion factor. Okay, where alpha is the adhesion factor and C dash is the cohesion of this layer, okay, along the length of the pile. Now, for cohesionless soil, this Fs becomes this K into sigma AB dash tan of delta. Okay, so K, what is K? K is the lateral earth pressure coefficient. Okay, and what is sigma dash AV? It is the average overburden pressure, average effective overburden pressure. Okay, and tan delta. What is delta? Delta is the wall friction between this pile material and the soil. Okay, and this soil actually. What is phi? Okay, what is phi? Phi is the angle of friction between the soil particles. Okay, and this delta is the angle of friction between this pile material and the soil. Okay, I hope you have understood. So delta can be defined as some k into phi. Okay, for different materials this k value is different. For concrete it is different, this k value is different. For acrylic or maybe steel this k value is different. Okay, it will change. Okay, so I hope you have understood all these things. So, and one thing I'd also like to mention that for for cohesionless soil, this QPU part, okay, this Q part is equal to sigma dash into NQ, okay, and this should be always less than equal to 11,000 kilonewton per meter square. Okay, there is a limit. Okay, it cannot exceed this. Okay. Uh, okay, so I hope you have all understood these things. If you have any doubt, you can please tell me. So if you have any doubts regarding anything, you can let me know. You can also write down in the chat box. If you have any doubts, please let me know. You can also write down your doubts in the chat box, or else I'll proceed to the problems. Okay. Okay. So I hope you have all understood these things. These are all basic things. So now I'm going to proceed to the problems. Okay. So let's go to the first problem. So this is the first problem. Okay, so the first problem is, let me read out the problem once. So a 15-meter long, 300 diameter pile is driven in a uniform deposit of sand. Phi is equal to 40 degree. The water table is at a depth of 2 meter below the ground level. The unit weight of sand above and below the water table is 18 and 20 kilonewton per meter cube respectively. Using k is equal to 2 and delta is equal to 3/4 of phi, NQ is given 135. Find out the ultimate load carrying capacity of the pile considering the critical depth concept. Take LC is equal to 20D for dense sand. Okay, so critical depth. Okay, so what is critical depth? Actually, till critical depth, it is considered while calculating the ultimate skin friction resistance, total skin friction resistance. It is considered that the overburden pressure, which is used to calculate the skin friction, it increases linearly up to critical depth, suppose up to 20D from the ground surface. Okay, but beyond that it will remain constant. Okay, so beyond that it will remain constant. So it is like this only. Okay, so you will understand it once again as I solve this problem. Okay, I have already explained these things previously in the previous sessions. So let me just say it once again. So suppose LC, it is mentioned over here that LC is equal to 20D. That is the depth of the critical depth. Okay, so that means from the ground surface up to 20D depth from the ground surface depth till that depth, the overburden pressure will increase linearly. After that, it will remain constant. Okay, and this is only required for calculating the skin friction resistance. Okay, so that's all. So you'll understand. Okay, as I solve this problem. So first of all, let me write down all the information that are given over here. So the length of the pile is 15 meter. So length of the pile is 15 meter, and the diameter of the pile is 300 millimeter. Dia is 300 millimeter. Okay, and it is driven in a uniform deposit of sand. Phi is equal to 40 degree. Okay, phi is equal to 40 degree, and the water table is at a depth of 2 meter below the ground level. Okay, suppose this is your ground level and this is your pile. It's like this. For example, vertical pipe, and it is 15-meter long. Okay, and the diameter is how much? 300 millimeter. Okay, and phi is 40 degree. The outer table is at a depth of 2 meter below the ground level, so that means 2 meter below the ground level. Here there is the water table. The unit weight of sand above and below the groundwater table is 18 and 20. So here gamma is how much? Here gamma is 18 kilonewton per meter cube, and here below the water table, this gamma set is how much? It is 20 kilonewton per meter cube. Okay, meter cube. Okay, and K is equal to 2, that is the earth pressure coefficient, and delta is equal to 3 by 4 of 5. So 3 by 4 of 40 degree, that means 30 degrees. Okay, and in Q is given, which is 135. In Q is 135, and LC is given. LC is 20D. Okay, so 20D means 20 into 0.3. It comes out to be 6 meter. Okay, so this is all the things that are given over here. And gamma W, that is the unit weight of water, is 10 kilonewton per meter cube. Okay, so let me draw this once again over here. This is the pile. The length of the pile is 15 meter. This is the ground surface, and at 2 meter depth there is a water table. Okay, and LC is how much? LC is 6 meter. Okay, so that means this is the critical depth. Suppose this is the critical depth LC. Okay, so up to this point, this overburden pressure will increase linearly. Okay, like this. Here it is 0 obviously, and here over here it is gamma into Z. Actually 6. Okay, it is 6, so that means this part is below the water table, the 4 meter. So up to here it will increase linearly, and below from this up to here it will increase linearly, and from here also below the water table it will increase linearly. Okay, and after that throughout the depth it will remain constant. Okay, like this. So up to here it will increase linearly, and from up to here it will increase linearly, and from here to here it will also increase linearly, and after that overburden pressure will remain constant. Okay, we must understand that we will use this concept only while while calculating the skin friction resistance. Okay, this critical depth concept. Okay, in science, obviously in questionless side. Okay, so what is the overburden pressure at this depth? What is the unit weight of the soil above the water table? So it is how much? It is 18, and below the water table it is 20. So here the overburden pressure is how much? 18 into 2, because the height is 2, the depth of the soil is 2, the depth of the soil is 2. This one is how much? This one is 4, and this one is how much? So 2, 4, and 4 plus 6 minus 15 is how much? 9. 9. Okay, 9. 2 meter, 4 meter, and 9 meter. Okay, so at this point, how much? So this unit weight is 18, and this unit weight into 18 kilonewton per meter cube, and below the water table gamma sat is how much? It is 20 kilonewton per meter cube. Okay, it is 18 and 20. Okay, so over here the unit weight is 18 into 2, that is 36 kilonewton per meter cube. 36 kilonewton per meter square. Sorry, meter square. Okay, because 18 into 2, this is 2, so 18 into, okay. And over here, what will be the overburden pressure at this depth, that is at 4 plus 2, 6 meter below the ground surface? So it will be this 36 plus 36 plus, this is submerged. Okay, this portion is submerged, this portion is above the groundwater table, and this portion is submerged. Okay, so for the portion above the water level, that is for the 2 meter portion, it is 36. So 36 plus, for this portion it will be gamma sat minus gamma w, that is the submerged, into 4 meter. Okay, so that means this saturated, how much? It is 20. So 20 minus gamma w, which is 10, into this 4. Okay, the 4 meter depth, it comes out to be how much? It comes out to be 76 kilonewton per meter square, and it is constant throughout the rest of the depth. Okay, so here it is 76 kilonewton per meter square, the overburden, effective overburden pressure. Okay, so we have determined the overburden, effective overburden pressures at various depths. So now let us go back to the question. So we need to find the ultimate load carrying capacity of the pile. Okay, so we need to find the ultimate load carrying capacity of the pile. So now, after determining all the overburden pressures, effective overburden pressures at various depths, we need to find out the frictional resistance part. Okay, that is the screen friction part. So for that, so what is the equation for to determine the skin friction, the ultimate skin friction? So so what is the equation for determining the ultimate skin friction along the length of the pile for cohesionless soil? I have written it over here. It is K sigma AV, that is the average effective overburden pressure into tan delta. Okay. So let me write that once again over here. So Fs, that is the unit skin friction resistance, it is K, that is the lateral earth pressure coefficient, or into sigma AV dash, that is the average effective overburden pressure into tan of delta. Okay, so this one. So now we need to find the skin friction along the length of the pile for various depths. Okay, that is for this portion, and this portion. Okay, for 2 meter portion, for 4 meter portion, and for the rest 9 meter portion. Okay, we need to determine the three or four. We need to determine skin friction for three length, for three segments. Okay, for three segments. So for the first segment, that is from 0 to 2 meter part, that is from top to, that is from here to here, that is 0 to 2 meter, this is 0 to 4 meter, and this is how much up to 15 meter. So for 0 to 2 meter part, for 0 to 2 meter portion, we need to determine the unit skin friction resistance. So we will use this for equation only, this equation. So fs1, okay, this is for 0 to 2 meter. Okay, so it is equal to this sigma av dash. Okay, so what is the sigma, that is what is the effective overburden pressure at 2 meter depth? It is 36. Okay, we have determined it, it is 36. Okay, this is sigma dash, and here it is sigma av dash, that means sigma of average. So that means we need to take the average. Okay, so see one thing over here. Here it is 36. Okay, and here it is 0. So what is the average? 0 plus 36 by 2. So sigma av. So what is k? And k is written over here, it is 2. Okay, k is 2, pressure coefficient. So k is 2. Okay, and sigma av is how much? It is 0 plus 36 by 2. Okay, for 0 to 2 meter depth, for this depth. So 0 plus 36 by 2. Okay, and tan of delta. Okay, so tan of delta is how much? We have already determined. Delta is 30 degrees. Okay, 30 degrees. If you calculate this, you will get the value of fs1. Okay, for the unit frictional resistance for the 0 to 2 segment, 0 to 2 meter segment. Okay, so if you calculate this, this fs1 will come out to be 20.8 kilonewton per meter square. Okay, so for the next segment, that is for the second segment, that is from 2 meter to 4 meter depth. Okay, so for 2 meter to 4 meter depth, fs2 2 meter to 4 meter depth. Okay, so for 2 meter to 4 meter depth, this fs2, you can write it like this. What is k? K is 2. We are using this formula only. So 2 into the average effective overburden pressure, that is sigma av dash. So what is sigma av dash? For this segment, for this portion, for at this depth, that is at 2 meter depth, it is 36, and for 4 meter depth, it is 76. Right? At this depth it is 36, and at this depth it is 76. Okay, we need to take the average. So 36 plus 76 by 2 divided by 2. For the top portion we use this 0 and 36, and for this portion we will use 36 and 76. Okay, so that means sigma av now, that is the average effective overburden pressure, is 36 plus 76 by 2, this one. Okay, into tan of delta. Delta is how much? It is 30 degrees. If you calculate this, fs2 will come out to be around 64.7 kilonewton per meter square. Okay, now for the third segment. Okay, for the third segment, that is for this segment. See, as I have told earlier, below the critical depth, for calculating this frictional resistance part, below the critical depth, it is considered that the effective pressure remains constant. Okay, so this is the critical depth up to this. uh, it is the critical depth LC up to 6 meters. So below that, the effective overburden pressure will remain constant. Okay, so over here the effective overburden pressure was 76, and it will remain constant throughout the rest of the depth. Okay, so that means at this point it is 76, and this point it will also be 76. Okay, so average, so sigma average at this point, sigma dash average at this point, it is the average effective overburden pressure at this point will be 76 plus 76 by 2. Okay, so fs3, that is the unit screen friction resistance for 4 meter to 15 meter part. So fs3 for 6 meter to 15 meter part, it is how much? So k, what is k? Wait a minute. So I hope you can see my screen. Okay, so let me get back to the problem once. Huh? So where was I? So yes, so fs2 is this. Okay, so now fs3 for 6 meter to 15 meter part. Okay, so 6 meter to 15 meter part. Okay, so we'll again use this equation. So k, what is k? K is 2, and now sigma av dash, so for this portion it is 76 plus 76 by 2. So 76 plus 76 by 2 into tan of delta. Okay, tan of delta is how much? Delta is 30 degrees. Okay, so delta is 30 degrees. So delta is 30 degrees. Okay, so now if you calculate this, you will get the value of fs3, and fs3 comes out to be around 87.8 kilonewton per meter square. Okay, okay. So now you have values of this unit skin friction resistance for the three segments of pile. So now we'll calculate the total ultimate skin friction resistance. Okay, so QF. So QF is what? QF is AS into FS. Okay, what is FS? What is AS? We have already calculated FS for three segments. Now what is AS? AS is AS for circular pile is pi into D into L. Am I right? So it is pi into D into L into Fs. Okay. So now there are three segments. Okay. So can I write like this? So pi into D, these are both constants. And this L into Fs, can we write it like this? 1 minute. We can write it like this, right? So L1 into Fs1 plus L2 into Fs2 plus L3 into Fs3. Okay, we can write it like this because there are three different segments and three different unit skin frictions. Okay, so we can write it like this, and we'll use this. So pi d into multiplied by L1 into Fs1 plus L2 into Fs2 plus L3 into Fs3, where L1, L2, and L3 are the lengths of three different segments. Okay, so for the first segment, so pi into d. So this is QF, total skin friction resistance. QF is equal to pi into d. Pi d, that is the diameter of the pile. So diameter of the pile is how much? It is 300 millimeter. So zero point 0.3. Okay, into L1 into Fs1. So L1 is how much? This segment, the first segment, it is 2 meter, 2 meter length. Okay, so and what is Fs1? Fs1 is 20.8. Okay, so 2 into 20.8. So 2 into 20.8, and L2 into Fs2. So what is the length of the second segment? This is the length of the second segment. It is 4 meter. And what is the skin friction unit skin friction resistance? Fs2, it is 64.7. So 64.7 into 4. Okay. And what is the third portion? Length of the third portion, it is 9 meter. And what is Fs3? Fs3 is 87.8. So that means that here it will be 87.8 into 9. Okay, so now if you calculate this, you will get the value of QF, and QF comes out to be 1028 kilonewton. Okay, and now for the total ultimate end bearing resistance. Okay, that is QB. We have calculated the first portion of the ultimate load carrying capacity. So the first portion, that is the total skin friction resistance, it is 1028 kilonewton. Now we'll calculate the ultimate end bearing resistance, that is QB. Okay, so QB is what? QB is AB into QPU. Okay, so AB into QPU. So AB, we know it is the cross-sectional area of the pile. Here it is a circular pile. And what is QPU? QPU sigma dash into NQ for cohesionless soil. Okay, sigma dash into NQ. So AB is pi by 4 into D square. The D is how much? It is 300 millimeter. That is 0.3 square. into this QPU. QPU is sigma dash into NQ. So what is sigma dash? Here also we will use this concept, the critical depth concept, because in the question it is already mentioned to use the consider critical depth concept. Okay, so for end bearing resistance also, for while calculating the end bearing resistance, we will also use this critical depth concept. Okay, so what is the effective overburden pressure at this depth? It is 76. Okay, so QPU, how much? It is QPU is sigma dash into NQ. So sigma dash is how much? It is 76. Am I right? And NQ, what is NQ? The bearing capacity factor. It is given in the question, I believe it is 135. So sigma into 135. Okay, now if you calculate this, you will get the value of QB, that is the ultimate end bearing resistance, and QB comes out to be around 725 kilonewton. Okay, one more thing I must say, this value of QPU should, or QPU, the small QPU should be less than, should always be less than 11,000 kilonewton per meter square. Okay, that means this portion. Okay, this actually this portion comes out to be around how much? Around 10260 kilonewton per meter square. Okay, that means it is okay. It is much lesser than 11,000 kilonewton per meter square. Okay, so after calculating QF and QB, so QF is 1028 kilonewton and QB is 7725 kilonewton. Okay, so that means the ultimate load carrying capacity, it is summation of both the parts QF and QB. Okay, QF and QB. So after adding these two terms, that is 1028 and 725, 1028 plus 725, you will get the value of the ultimate load carrying capacity of the pile. Okay, so it comes out to be 1753 kilonewton. Okay, so I hope you have understood this problem. So please let me know if you have understood this problem or not. Please let me know if you have understood this problem or not. Please go through this problem for a couple of minutes. So please go through this problem for a minute, and after that I will proceed to the next problem. And if you have any doubt, okay, so how do you calculate the critical depth? It is not given in the question. Okay, it is a very good question. It is a very good question. See, if you are asked, you generally consider this critical depth. Remember this thing: for loose sand, this LC critical depth is generally taken as 15D. Okay, and for dense sand, this ALC is taken as up to 20D. Okay, so for loose sand LC, the critical depth is around 15D. 15 into this D is the diameter of the pile, and for dense sand, the critical depth is around 20 times the diameter of the pile. Okay, so I believe I have answered your question. Please let me know if you have any more doubts. Please let me know if you have any more doubts, or shall I proceed to the next problem? And please remember the critical depth for loose sand and dense sand. Okay, it is 15 times the diameter of the pile for loose sand, and it is 20 times the diameter of the pile for dense sand. Okay, so there are no more questions, and if you have any more questions, you can always post your doubts in the NPTEL forum, and also you can post your doubts in the YouTube comments section, because all the recorded lectures are available on YouTube, and you can also post your doubts over there. And you can also personally mail me, because the mail ID is given on the description box, in the description box of YouTube videos. Okay, so let me proceed to the next one, the next question. So the next question is this: estimate. So the next question is this: so estimate the safe load carrying capacity. The safe load carrying capacity of a single boat pile of 25-meter long, that is, the length is 25-meter long, the length of the pile, 500 diameter, diameter is zero point 0.5 meter, the factor of safety is 2.5, factor of safety is 2.5, and the strength of different soil layers is as follows. Okay, so the length of the pile is 25-meter, and up to 30-meter depth below the ground surface, the ground condition is given. Okay, the undent shear strength, that is undent cohesion, Cu. Okay, it is given. Okay, this is okay. It is given. Cu is given, so it is, so up to 30-meter depth is given. Addition factors are also given. Okay, so you need to estimate the safe load carrying capacity of a single boat pipe. Okay, so let's get started. So here, so QU, first of all, we need to determine the ultimate load carrying capacity of the pile. So after determining the ultimate load carrying capacity of the pile, that is QU, we can divide that by factor of safety to determine the safe load carrying capacity. Okay, so first of all, we need to determine QU, and after that we will apply factor of safety on that to determine the safe load carrying capacity. Okay, so for determining, so we need to determine QU first. So for determining QU, we need to determine QF and QPU or QB respectively. Okay, we need to determine both the terms. Okay, QPU or QB, any the two terms can be used interchangeably. Okay, and this QB or QPU, both these two variables are same. Okay, so both these two are the total end bearing resistance. Okay, QBU and QPU. You can use either one of them to represent the total end bearing resistance of the pipe. And this QF, capital QF, is the total skin friction resistance. Okay, so now we will determine QF. Okay, first we'll determine QF. So QF, here it is cohesive soil. Okay, Cu is given, undent shear strength Cu, it is given, so it is cohesive soil. Okay, so QF. So for cohesive soil, QF is what? So for cohesive soil, QF, it is S into Fs, right? QF is generally Fs into S, and for cohesive soil, this Fs. What will be Fs? Fs is Fs is alpha into C dash. Okay, that is the let me draw it once, you will understand. Suppose this is your pile and this is resting on a farm strata. Okay, so this C dash, or C dash, is the cohesion of this portion, okay, of this soil layer along the length of the pile. Okay, and CP is the cohesion of this portion that is below the pile tip. Okay, cohesion of the soil below the below the pile tip. Okay, that is CP, and cohesion of this soil portion that is along the length of the pile, it is denoted by C dash. Okay, so QF is AS into alpha into C dash. Okay, so now we can also break it like we did in the previous question. Okay, while in the previous problem we we can break it like this. Okay, so how we will break it? So like we did in the previous question, in the previous problem, like this. Okay, we'll use this concept over here also. See, so 25 meter, the length of the pile is 25 meter, and up to 30 meter the information are given. Okay, the data are given. So let me draw the pile over here once. So suppose this is your pile, the length of the pile is 25 meter, and what are the segments? So first segment is 0 to 5. Okay, so 0 to 5. So suppose 0 to 5 meter. So 5 meter is the length of this segment. The next segment is 5 to 10. Okay, so 5 to 10. So 0 to 5 meter, and here it is 10 meter. So that means the length of this segment is also 5 meter, and the third segment is 10 meter to 20 meter. So for 10, from 10 meter to 20 meter. Okay, so this segment is how much? 10 meter, the length of this segment, and the length of the pile is 25 meter. So that means up to this portion we will consider. Okay, to up to 25 meter. So this segment is 5 meter, the length of this segment. Okay, so up to 30 meter data is given, and this. Okay, so we'll use this data for this segment. Okay, for this. So now, so we have divided the pile into 4 segments. Okay, 5 meter, 5 meter, 10 meter, and 5 meter. These are the lengths of the respective segments. Okay, so now let me write it like this. So QF is equal to AS alpha into C dash. Okay, so QF is equal to AS alpha into C dash. Okay, so can we write it like this? So AS is what? AS is pi into D into L. So pi into D, that is surface area of the pile, pi into D into L, and this one is alpha into C dash. Alright. So pi into D is constant. Okay. So can we write it like this? L1 is the length of the first segment. Addition 1 is the addition factor of the first segment, and C1 is the undent cohesion of the first segment. And there are 4 segments. Okay. So we can write it like this, right? L4 alpha 4 C4. Okay, we can write it like this. See, these are the lengths L1, L2, L3, L4. 5 meter, 5 meter, 10 meter, 5 meter. These are the lengths. Alpha 1, alpha 2, alpha 3, alpha 4. Addition factors C1, C2, C3, and C4. Okay, everything is given. So so now let me just incorporate. So let me just put all the values into this equation. So pi into what is the diameter of the pile? Diameter is how much? It is 0.5. So pi into 0.5 into L1 alpha 1 C1. Okay, so length of the first segment. It is how much? It is 5 meter. So 5. What is alpha 1? Alpha 1 is 1 and C is 25. So 1 into 25. Okay, plus L2. L2 is how much? 5 meter, and alpha 2 is 1, and it is 38. Cu is 38. Okay, so it is 5 into 1 into 38 plus L3. What is the length of the length L3? L3 is 10 meter, the length of the third segment, and addition factor is 0.8 and Cu is 50. Okay, so here it is 10 into 0.8, the addition factor, into 50 is the cohesion value. Okay, and for the third portion, that is for the fourth portion, the length is L4 is 5 meter, addition factor is 0.4, and cohesion is 100. Okay, so that means 5 into zero point 0.4 into 100. So now if you calculate this, you will get the value of QF, which comes out to be around 1437 kilonewton. Okay, so we have determined the value of ultimate skin friction resistance. Okay, so now we have determined this part, the frictional ultimate frictional resistance of. Okay, so now we'll determine this part, that is the ultimate end bearing resistance. Okay, total end bearing resistance. So QB is what? It is AB and into small QPU. Okay, small QPU is the unit end bearing resistance, and for cohesive soil, this QPU is can be written as 9 CP. Okay, so this becomes AB into 9 CP. What is CP? CP is the cohesion below this pile tip, cohesion of soil layer below the pile tip. Okay, so up to 30 meter data is given. So we will use the CP of this layer over. So we will use the CP of this layer. Okay, because the CP is same from 20 meter to 30 meter, I believe. Okay, see, CP is same, that is the cohesion is same from 20 to 30 meter. That means the cohesion is same from this layer up to 30 meter. Okay, the cohesion is same, so we can use this cohesion only 100. Okay, so cohesion is 100, and okay, okay, no addition factor is needed. So AB is uh, uh, the cross sectional area of the pile. So pi by 4 into d square. What is d? What is the diameter of the pile? Diameter of the pile is 500 millimeter. That is 0.5 meter. 5 square into 9 cp. 9 into cp is how much? It is 100. Okay. Now, if you calculate this, you will get the value of QB, that is the total end bearing resistance, and it comes out to be around 177 kilonewton. Okay, so now you have both the parts. So you both the parts, that is the ultimate skin friction resistance and ultimate end bearing resistance, and you need to add up both the terms in order to get the total load carrying capacity or the ultimate load carrying capacity of the pile. So QU is equal to QB plus QF. So QB is how much? It is 177, and QF we have already determined over here. It is 1437. So 1437. So if you add both the terms, it is how much? It comes out to be around 1614. 1614 kilonewton. Okay. So in this question, we have been asked to determine the safe load carrying capacity, and factor of safety is also given 2.5. Okay. So Q safe is how much? We need to apply factor of safety on this value, that is 1614, the ultimate uh, load carrying capacity of the pile. So QSF is equal to QU by FS. So QU is 1614, and the factor of safety is 2.5, and it comes out to be around 645.6 kilonewton. Okay, so this is the safe load carrying capacity of the pile. Okay, so let me know if you have any doubt. Please go through this problem once, and please let me know if you have any doubt in this particular question. Please let me know if you have any doubt in this particular problem. Please go through this problem once. I'm giving you a couple of minutes. Please go through this problem. So I believe you have no doubts. So let me proceed to the next problem. So this is the third problem. So a concrete pile, it is a square concrete pile, 305 millimeter by 305 millimeter in cross section is driven to a depth of 20 meter below the ground surface in a saturated clay soil. Okay. A summary of the version of frictional resistance FC is obtained from cone penetration test is as follows. So we have cone penetration test data over here, and we need to estimate the frictional resistance for the pipe. So we have been asked to estimate only the QF part or QS. Okay, QF can also be represented by QS. So we need to estimate the frictional resistance part. And here the cone penetration test data is given CPT. Okay, from CPT test we get this frictional resistance. Okay, kg of FC. Now remember one thing. Uh, Remember one thing. This. So what is QF or QS or QS? It is a saturated clay soil. So what is QF or QS? It is ASFS, right? So ASFS, it can also so AS into FS. Okay. Now this FS, what is FS? FS is the unit skin friction resistance, right? Unit skin friction resistance. Okay. So what is Fs? Fs, we generally write it like this. For clay, it is alpha into C dash, right? Alpha is the addition factor and C dash is the cohesion part, as I have explained earlier. C dash is this, the cohesion of this soil portion along the length of the pile, right? Okay, so this one, okay, this one is Fs, and for CPT data, this Fs becomes alpha dash addition factor, okay, addition factor multiplied by another, this one is another addition factor, no, not this, okay, this one is alpha, this one is alpha dash, a different addition factor multiplied by FC, that is this term, okay, FC. So before going into these terms, let me explain what are these addition factors, what are these factors actually, alpha and alpha or alpha dash. See, so suppose see, this is a pile, right? This is a pile and this is your soil. Okay, so this C dash is the cohesion of this soil layer along the length of the pile, okay, of this soil layer. But there will be adhesion between this pile material and this soil along the length of the pile, okay. So this adds, there will be adhesion, okay, between this soil and the pile material along the interface, along this interface between pile and soil material, okay. And that adhesion, that force of adhesion is a factor of cohesion, okay. So that factor is known as alpha. That is why it is represented as alpha into C, okay. Okay, so now let me get back to the problem. So it is alpha dash into FC. So Fs is equal to alpha dash into FC. That is unit in skin friction resistance. Fs is equal to alpha dash into Fc, where Fc is this, the frictional resistance that we get from CPT test data. And these are in kg per centimeter square. So let me just transform this into kilonewton per meter square. Let me write it down over here, all this data. So 0 to 6 meter it is 0.35, 6 to 12 it is 0.56, from 12 to 20 it is 0.72, all in kg per centimeter square. Okay. So let me write it down over here. For 0 to 6 meter depth, the FC FC is 34.34. All these are in kilonewton per meter square. Okay, 0 to 12 meter, it is 54.94 kilonewton per meter square, and for 12 to 20 meter, it is 70.63 kilonewton per meter square. Okay, and now we need to determine this alpha dash. Okay, how will it determine? We will use this curve. Okay, this curve for concrete and timber piles. We will use this curve because the pile is uh, we are assuming that it is a concrete pile. Okay, because yes, it is mentioned over here, a concrete pile. So we will use this curve for concrete and timber piles. Okay, so we need to determine FC and PA. FC by PA. Okay, so FC, we know the value of FC. These are the value of FCs. These after converting into kilonewton per meter square. And what is PA? PA is a reference pressure. We generally take it as atmospheric pressure or 100 kPa. That is 100 kilonewton per meter square. Here PA is 100 kilonewton per meter square. It is the reference pressure. Okay, so FC by PA. So that means for the first part, for the first segment, FC is 34.34 and this PA is 100. So 34.34 by 100 is how much? 0.34. So 0.34 generally comes over here. Okay. So if we draw a line like this, and if we extrapolate, if we just draw it like this, if we just project this point over here, we'll get the value of alpha dash. So alpha dash is how much? It is near about 0.84. So alpha is 0.84 for the first segment, and for the second segment, FC is how much? 54.94. So 54.94 divided by PA. PA is how much? 100. So 54.5. So 54 becomes 0.54. So 0.54 is over here. Suppose if we project it like this and then we project that point over here, we'll get the value of what? We'll get the value of alpha dash for the second segment. So it is around 0.71. Now for the third segment, the FC value is 70.63 and PA is 100. So FC by PA becomes 0.7. Okay. So now if we just, zero point 0.7 is somewhere over here. So if we just project this line like this and project that point over here, we will get the value alpha dash. It is around 0.63. See, 0.63. So we have the values FC and alpha. So we know the value of FC and alpha dash. For from this curve we get the value of alpha dash. Okay, so we know the FC for three different segments, from for 0 to 6, 6 to 12, and 12 to 20. We also know now the value of alpha dash, that is the addition factor for these three segments, and pile length is also 20 meters, up to 20 meters. So that is all. So we know the FC, we know the value of FC and alpha dash for all the segments. Now we need to just calculate the frictional resistance, that is QS. So QS is what? QS is Fs into AS. AS what is? This is the surface area of the pile, which is pi into D into L. So QS is equal to Fs into AS. Okay. So we need to also break it like break this up like the previous problems. So AS is pi into D into L, and Fs. So that we can break it like this. So there are three segments. There are three segments: 0 to 6, 6 to 12, 12 to 20. Okay. So 0 to 6 is how much? 0 to 6 is 6 meter. 6 to 12 is also 6 meter length. These are the lengths, and 12 to 20 is 8 meter. These are the lengths. Okay, L values. So we can write it like this. Wait a minute, please. Okay, so let me write down that once again. So 0 to 6 meter, the length is 6 meter. I hope you can see my screen. And for 6 to 12 meter, it is 6 meter. And for 12 to 20 meter, the length is 8 meter. These are the lengths of the segments. Okay. So for the first segment, so we can write it like this: pi into d into L as into fs. Okay. So you can break it like this: pi into d into L1 into fs1 plus L2 into fs2 plus L3 into fs3. Right? We can break this into three segments. So pi into d, the diameter of the pile, it is how much? It is 305 millimeter. So that means 0.305 meter. So 0.305. Okay. L1, the length of the first segment is, it is how much? It is 6 meter. 6 into fs1. Fs1 is how much? It is this fs1. This fs1 is alpha dash into fc. Okay. This fs is equal to alpha dash into fc. Okay. So 6 into fs1. Fs1 is how much? It is alpha dash into fc1. Alpha dash into fc1. Alpha dash is how much? It is 0.84 into 34.34. 0.84 into 34.34. So 34.34 into 0.84. Okay. For the second, this part, it is L2 is how much? It is 6 meter into alpha dash 2 into fc2. Fc2 is how much? 54.94 into 0.71. So 54.94 into 0.71 plus the third term. The length of the third photo segment is how much? It is 8 meter. So 8 into alpha 3 into fc3. Alpha 3 is 0.63, and so 0.63 into fc3 is how much? It is 70.63. So if you calculate this, you will get the value of total skin friction resistance. So after calculating this, you will get the value of QF, that is the total skin friction resistance. So QF comes out to be around 1 minute. Actually, one thing, I'd like to mention one thing. This is a square pile, sorry, not a circular pile. So here AS, actually here FS into AS. So what is the surface area of a square pile? So surface area of a square pile AS is generally taken as 4 into the side of a square. So perimeter of a square, it is 4 into so no yes, so it is side of a square, it is the perimeter. So AS is equal to perimeter into length. So perimeter is how much? 4a into length, the total length of the pile. Okay. So we will use not pi into d. In place of pi d, we will use 4 into the side. Suppose b. Suppose b. Okay. Let me write it down clearly. Uh, the surface area of a square pile is generally the perimeter of the pile into the length of the pile. Okay. The perimeter is how much? Perimeter is 4 into b. That is the b is the dimension, the length of a side of a square into length. 4 into b into l, suppose. Okay. So b is how much? Suppose it is 0.305. So b is here 0.305 meter. Okay. So it is how much? 4 into b into l. Okay. So 4 into b into l into fs, and we can break it like this. So here it will be 4 into b. Okay. So in place of uh, pi, there will be 4. So 4 into b into this. Okay. So now if you calculate this, you will get the value of qb. Okay. The qf, that is the total skin friction resistance. So it will come out to be around 931 kilonewton. Okay. So please let me know if you have understood this or not. Please let me know if you understood the concept or not. Please go through this problem once. Please go through this problem for a couple of minutes and let me know if you understood the problem or not. Yes, don't worry. This alpha dash, the value of alpha dash will be given or the graph will be given. Okay. The value of alpha dash will be given in the examination. Okay. Not to worry about that. Don't worry about that. So shall I proceed to the next problem? Please let me know if you have any doubt. Okay, so now let me proceed to the next problem. So let me read out the problem once. So a concrete pile of 45 centimeter diameter. Okay, so diameter is 45 centimeter or 0.45 meter. So a concrete pile of 40 centimeter diameter was driven into sand of loose to medium density. Okay, so this pile was driven into sand of loose to medium density to a depth of 15 meter. Okay, so depth of the pile is how much? It is 15 meter. The following properties are known. The average unit weight of soil along the length of the pile. The average unit weight of soil along the length of the pile, gamma is how much? 17.5 kilonewton per meter cube. Average phi is 30 degrees. Average Ks is 1 and delta is 0.75 of phi. Calculate the ultimate bearing capacity of the pile. Allowable load with factor of safety 2.5. Assume the water table is at a great depth. Use Beres-Anseb's method. Okay, so we have been asked to calculate the ultimate bearing capacity of the pile. Okay, And after that, we need to calculate the safe load or the allowable load by applying factor of safety. Okay, and water table is at a great depth. Okay, so for determining this ultimate bearing capacity of the pile QU, we need to determine the skin friction resistance and the total end bearing resistance, that is QPU and QF, right? So we'll determine these two terms and we'll sum it up. Okay. So first of all, we'll determine this part. So okay. So let us proceed. So what is the phi? Phi is 30 degrees. Okay. So the phi is, let me, okay. So let me just break this into, okay. So QU is what? QU is capital QPU, that is the total end bearing resistance, and unit skin friction resistance. Okay. So we can also write it like this, QPU. So what is QPU? Capital QPU is AB, that is the cross section area of the pile, multiplied by small QPU, that is the unit end bearing resistance, and QF is what? AS, that is the surface area of the pile, into the unit skin friction resistance, that is FS. Okay. Now we can write QP, this one. We can write it like this again. So this is a cohesionless soil, loose to medium density of, it is a sand of loose to medium density. So AB, that is the cross section area of the pile, into QPU. So QPU for sand is what? For cohesionless soil, it is sigma dash into NQ, right? And AS is the surface area of the pile. And what is FS? FS is K into sigma AV dash into tan delta. Am I right? We have already explained this term. I have already explained these terms in the previous problems. So I am breaking this. So QPU, I am just substituting all the terms. Okay. So QPU is this and QFS is this. Okay. So we will use this chart. We will use this chart to determine this NQ part. Okay. This NQ. So what is the length of the pile? Length of the pile is 15 meter. Okay. 15 meter. So we need to determine L by D ratio first. Okay. So L by D is how much? 15 divided by the diameter of the pile. Diameter is how much? 45 centimeter. Okay. That is 0.45 meter. Okay. So it generally comes out to be around 33.3. Okay. So L by D is 33.3, and phi. We also need phi. Phi is how much? Phi is 30 degrees. Okay. 30 degrees. Okay, so there is no curve for 33.3 L by D 33.3, but it will lie somewhere between these two curves. Okay, this curve is for L by D equal to 20, and this curve is for L by D equal to 70. So L by D 33.3 will somewhere lie between these two curves. Okay, somewhere over here. So for L by, so for 30 degree, corresponding to 30 degree, this is the value of NQ. Okay, so NQ for L by D 33.3, it is, if we look at the graph, NQ, it comes out to be around 16.5. Okay, It comes out to be around 16.5. Okay, so now let me just use this equation to determine the value of ultimate load carrying capacity or ultimate bearing capacity of the pile. Okay, so we need to determine, we have already determined NQ, we need to determine Q dash. AB is the cross section area of the pile. So AB is what? AB is pi by 4 into d square. D is diameter of the pile, how much? It is 45 centimeter. So 0.45 pi by 4 into d square. It comes out to be around 0.159 meter. Okay, meter square. And what is the surface area of the pile? AS, this AS is how much? It is pi into d into L, pi into d into L. So pi into 0.45 into length of the pile is how much? It is 15 meter. So 15. So it comes out to be around how much? 21.195 meter square. Okay. So now we have determined this term, and this term. Okay. So we need to determine this sigma dash and sigma AV dash. Okay. So sigma dash at 15 meter depth. So sigma dash at 15 meter depth. It is how much? So water, since water table is at a great depth, there is no need to consider any submerged unit, just gamma into L. So gamma is how much? 17.5. So 17.5 into 15 meters. It comes out to be around 26.2, 262.5 kilonewton meter square. Okay, actually the effective overburden pressure increases like this. It is gamma into L from 0 to 15 meter. It linearly increases, and sigma AV dash at 15 meter is equal to this sigma L at 15 meter is 262.5, and here it is 0 at 0 depth, that is at the ground surface. So the average is 0 plus 262.5 by 2, and it comes out to be around 131.25 kilonewton per meter square. Okay, so now you have determined all the terms, the sigma dash, this sigma AV dash. Okay, we know the value of K. Okay, now tan delta. This delta is how much? Delta is 0.75 of phi. Phi is how much? 30 degrees. Okay, so this is the value of delta. Okay, delta, so it comes out to be around 22.5 degrees. So we can easily find tan delta. So we have this also, we have this, we have this, we also have this. So we know the value of all the parameters, right? We also know the value of NQ, sigma dash, and AB, that is the area of the base of the pile. Okay, we know everything. So now if we just put all the values of all the parameters into this equation, we will get the value of QU. Okay, so after calculating, QU comes out to be around, after putting all the values, QU comes out to be around 1841 kilonewton. Okay, this one is the answer. If you just put the values of all the parameters, so we have determined all the parameters, and some parameters are also given. Now if you put the values of all the parameters into this equation, you will get the value of QU, which is 1841 kilonewton. Now we need to use this factor of safety to determine the allowable load. Okay, so Q allowable or the safe load is QU by factor of safety. Q is how much? It is 1841. Factor of safety is how much? It is 2.5. So it comes out to be around 736 kilonewton. Okay, so this is the answer. Please let me know if you have understood this problem or not. If you have any doubt, you can also let me know. Please go through this problem for a couple of minutes and let me know if you have any doubts in this problem. So shall I proceed to the next problem? Please let me know if you have any doubt. You can also post your doubts in the forums, and you can also post your doubt in the YouTube chat box, because these lectures will be made available. This lecture, the current lecture will be made available, and the previous lectures are already available on YouTube. Okay, so let me proceed to the next question. Okay, so this is the question number 5. So here, assume in question number 4 that the water table is at the ground surface. Okay, so assume in question number 4 that the water table is at the ground surface. Saturated unit is given. It is 18 kilonewton per meter cube. All the other data remain the same. Calculate Q ultimate and Q allowable. So in this particular question, we have been asked to refer this question, but the water table is at the ground surface. Okay, but the water table is at the ground surface. So that means, so the pile is of 15 meter and the diameter is 45 centimeters. So it is like this. In this particular question, the water table is at a great depth, and in this particular question, water table is at the ground surface. Okay, so that means water table is over here. Water table is over here, and the pile. Here is a pile. The length is 15 meters, and the diameter is 45 centimeters. Okay, this is the problem. So saturated unit weight is given, gamma sat. It is 18 kilonewton per meter cube. Okay, we need to calculate QU and Q allowable. So I need to calculate QU and Q allowable. Okay. So QU is what? It is QF plus QPU or QB for. Okay, so QU, the ultimate bearing capacity, can be represented into by these two terms, QF and QPU, and this is sand. So QF can also be written. So QF, we can write it like this, like we did over here. Okay, so this QF, capital QF, is AS into FS plus QPU is QPU into AB. We can write it like this, and AS, this FS can be written as K sigma AB dash into tan of delta, and QPU can be written as sigma dash NQ, and AB is the cross-sectional area of the pile. Okay. So now AS, what is AS? AS is the surface area of the pile. We have determined, since the dimension is same, we have determined the value of AS over here. AS is 21.195. So AS is 21.195 meters square, right? So we have the value of this parameter. What is AB? Since the diameter is different, since diameter is same actually, since the diameter is same, we can use this AB also, the value of this the cross-sectional area of the pile, which is 0.159 meters square. So AB is 0.159 meters square. Okay, so we have the values of these two parameters. Well, we also know the value of K. It is similar to that of the previous question. K is 1. We also know the value of tan delta. We also know the value of NQ because NQ depends upon L by D and phi only. NQ depends upon L by D and phi only. So NQ is 16.5. So NQ is 16.5. So we also know the value of this one. And K, let me write it down over here. So K is 1 and 10 and delta is 22.5. Okay. Delta is 22.5 and K is equal to 1. Delta is 22.5 degrees and K is equal to 1. Okay, so we just need to determine this sigma dash AV and sigma dash at 15 meter depth. Okay, so sigma dash at 15 meter depth, that is the effective overburden pressure at 15 meter depth. Since this is totally submerged, okay, this is totally submerged, we need to use the submerged unit weight. Okay, so saturated unit weight is 18, saturated unit weight is 18, and so what will be the effective overburden pressure at 15 meter depth? It is totally submerged. So we can write it like this. The saturated unit weight is 18. So we can write it like this. Gamma sat minus gamma W into 15. So gamma sat is how much? It is 18. Gamma W is 9.81 and it is 15 meter length. And it is also increasing linearly, right? It is also this sigma dash, the effective overburden pressure, it increases linearly from the ground surface to 15 meter depth. Okay, in both the cases, it does not depend upon water table. Okay, actually, in the first case, the water table is at a great depth, and here the water table is at the ground surface. Okay, so if the water table was somewhere in the middle, then it would have been different. But since the water table is at the ground surface, then it will also increase linearly from 0 to 15 meter depth. That is from ground surface to 15 meter depth. Okay, so yeah, so that means sigma dash at 15 meter depth is how much? It is around 130. If you calculate this, you will get sigma dash around 130.35 kilonewton per meter square. Since this is also increasing linearly, so sigma dash average at 15 meter depth is 0 plus 130.35 by 2. So 0 plus 130.35 by 2. And it comes out to be around 65.18 kilonewton per meter square. Okay. So we have determined this QAV dash and Q dash. Okay, so now you have the values of all the parameters. We know AS, AB, we know the surface area, we know the value of the cross-sectional area of the pile, we know the value of K, that is the lateral earth pressure coefficient. This, we know the value of tan delta, we know the value of delta, you can easily apply tan. Sigma dash, we know the value of sigma dash at 15 meter depth. We also know the value of sigma AV dash. Okay, we know NQ. Okay, so we have everything. So we have the values of all the parameters. You just need to put all the values into this equation. So after calculating, you will get the value of QU, which comes out to be around 914 kilonewton. Okay, so after applying the factor of safety, what is the factor of safety? It is 2.5. Factor of safety is 2.5 in the previous question. We need to use that. So Q allowable or Q safe is QU by factor of safety. So 914 by 2.5, it comes out to be around 366 kilonewton. Okay, so this is the answer. One thing you must notice, this in submerged condition, the ultimate bearing capacity is 914 kilonewton. Okay, and when the water table is at a great depth, it is 1841 kilonewton. Okay, so that means when the water table is at the ground surface, in that case the ultimate load carrying capacity of the pile decreases by almost about 50%. Okay, here it is 914, and when the water table was at a great depth, at that point of time, the ultimate load carrying capacity was around 1841. It is almost double. It is almost double. Okay, see, here it is 914, and here it is 1841 in this case, in the dry case. And here the water table is at the ground surface. In this particular case, QU is 914. Okay, so water table. So here it is almost half to that of the dry case. So what I'm trying to say is that the ultimate bearing capacity of the pile becomes half when the water table is at the ground surface. Okay, so please let me know if you understood this problem or not. So please let me know if you understood this concept. Please go through this problem for a couple of minutes and let me know if you have any doubt in this particular question or not. Please let me know if you have any doubt in this particular question. You can also ask your doubt later in the YouTube comment section or on NPTEL website, on the NPTEL forums. You can also ask your doubt over there. Okay, so I believe you don't have any doubt currently. You can always post your doubt later. And so this is the last question of today's session, and prepare well for the examination, which is coming. Examination is about to come, so prepare well for that. And if you have any, if you face any doubt regarding preparation, regarding any topics of this advanced foundation engineering course, you can ask me by mailing or by posting your doubts on the forum. And prepare well for the examination. And since today is the last session, I want to tell you that I have enjoyed a lot while solving this problems, while explaining these problems to you guys. I have enjoyed a lot, and I believe we will meet in some other courses. And so all the best for your examination. Bye for now, and prepare well for the examination. Okay, so goodbye and all the best. You may log off now. Thank you. Thank you for attending this session. Okay, goodbye.